Hello. Today let's talk about the trajectory of motion under central force. Under gravitational central force, essentially. For example, the trajectory of an asteroid rotating about the sun, or the trajectory of a satellite rotating about the Earth. So by now, in another video lecture, if you go back, I have talked about the trajectory of motion under central force. To remind you, the trajectory of motion under central force, under a central force, is described in this equation of motion. Again, to remind you, the equation of motion describes the trajectory of motion as a result of a forcing function. We use polar frame, and for a planar motion, we have developed this equation of motion for a central force. In this equation of motion, we have h0 squared equal to capital H0 over m. H0 is our specific angular momentum. And to remind you again, h0, which is our angular momentum, by definition, angular momentum is equal to moment of translational momentum. So what is translational momentum? Translational momentum is simply mass multiplying velocity. And velocity in radial transverse frame is simply r theta dot. So you can figure out how you would arrive at this relationship for angular momentum, or you can go back and look at the other video lecture about motion under central force. So now in this video, let's go back to our objective. So we are interested in the trajectory of motion under gravitational central force, a specific type of central force. And in this specific type of central force, the force is described as G, capital G, M over R squared. G is our universal gravitational constant. R is the distance between the asteroid and the center of the sun. And capital M, so for example, if you're interested in the motion of the asteroid about the sun, capital M is the mass of the sun, and small m is the mass of the asteroid, and R is the distance from the center of the sun to our asteroid. And if this was describing the motion, the force between the Earth and a satellite which orbits about the Earth, then this mass, capital M, is the mass of the sun, and M is the mass of your satellite or a spacecraft, and R is the distance to the center of the Earth from your rotating mass. Once we replace this F with this description of F for this specific kind of central force, then what happens is that this R squared cancels with this R squared. So we end up having this equation of motion. What is the good thing about this? Good thing about this equation of motion is that now on the right hand side, if you pay close attention, we don't have any R. The parameter R does not appear on the right hand side. So which is a really good thing, because now we end up having a linear second order ODE, second order ordinary differential equation, with a constant right hand side. So because this is simply second order ordinary differential equation, and it's a linear differential equation. So to remind you from your ODE course, the solution of a second order differential equation, ordinary differential equation, is the sum of particular solution and homogeneous solution. The particular solution looks like your right hand side. So in this case, we have a constant right hand side. So our particular solution would be gm over h0 squared. So this is our particular solution. And then plus capital C cosine theta minus theta 0, and this is your homogeneous solution. So let me just say homogeneous solution or homogeneous solution. I have seen them. I have seen it called both in different textbooks. So, and you know that when you have a second order ODE, the solution is gonna have two constants, which are to be determined using your initial conditions. So we have this unknown C and this unknown theta 0, which are to be determined using initial conditions. Just one side point here. I've realized that occasionally students having difficulty with this ordinary differential equation because it is not with respect to time. So it is exactly the same equation. If instead of theta we had time, we would have solved this equation. We would have solved 1 over r as a function of time. In this case, we have theta, so we solve it in terms of theta. So the solution is the sum of particular solution and homogeneous solution. It is a pretty standard second order ODE, so you already know that the solution is a cosine function or a sine function, depending how you describe the solution. So we have C cosine theta minus theta 0. Now what we do here is that we said that for any solution of any second order ODE, we need to apply initial conditions and determine the unknowns. In this case, what we're going to do to make our life easier, so we're going to set the initial position to be at point A, and because theta 0, is the initial angular position in our polar frame. Remember that when we derived the equation of motion for motion under center of force, we did it in that radial transverse frame. So theta 0 is initial angular position with respect to this horizontal axis. If I set my initial position to be point A, theta 0 is going to be equal to 0. And A is the closest approach to the center of rotation. And in orbital dynamics, this A is called preapsis. And we are going to talk about preapsis and apoapsis, which is the farthest point from the center of rotation. So A is preapsis, and if you start our motion from this point, this theta 0 goes to 0. All right, so our equation, so finally, this is what we have, the trajectory of motion. 1 over r is equal to gm over h0 squared plus c cosine theta. All right, fantastic. So I'm going to factor out gm over h0 squared and describe the equation in this one. 1 plus epsilon cosine theta. And if I do it this way, then I can describe qualitatively, I can describe all the different types of trajectories of motion in terms of our epsilon. Epsilon is called eccentricity. So now, if I would suggest that you plot this equation, this relationship, and you're going to see that what you get for different epsilon. So for example, if epsilon was equal to 0, you're going to get a circle for your trajectory of motion. This case should be pretty obvious. If you go back to your polar frame, to a radial transverse frame, then if I set epsilon equal to 0, 1 over r is going to be equal to constant. So r is going to be equal to a constant, which describes the circle in our polar frame. So we're going to talk also about other cases. If epsilon was less than 1, we're going to get an ellipse. The special case for an ellipse is when epsilon is equal to 0, and we get a circle. And if epsilon was larger or equal to 1, you're going to get a parabola or you're going to get a hyperbola. So essentially, it's not anymore a closed orbit. So next time, we're going to talk about this. What happens when the velocity of your rotating mass goes or transitions from a certain number to a larger number. In other words, we're going to find or compute a velocity which is called a critical velocity, and we're going to show that for velocities larger than that number, your orbit is not going to be anymore a closed orbit. So next time we're going to compute that critical velocity, which is called escape velocity, and discuss various types of trajectory of motion. All right, see you next time.